Before we start talking about general amplifier circuits and that type of thing, we're going to cover a little bit about just signals in general, since all electronic circuits are going to process some type of signal. So, when there is an amplifier or a rectifier, which basically can take positive and negative voltages and make them all positive, that kind of thing, everything processes some type of input signal. And the input signals are going to be modeled in one of two ways. We're either going to look at a practical voltage source in which we have some source voltage with a series resistance, and we usually use this form if the series resistance is relatively low. For a current source, we might use that, and we would use a current source if the series resistance was rather high. Usually we use practical voltage sources more than anything in here, but one or the other will be representing the signal going into the circuit. In circuit analysis, we generally deal with ideal sources, but in electronic circuits, it makes more sense to use practical sources. Ideal sources have no series resistance or parallel resistance, but a practical source will always include some type of source resistance, and that can actually have an effect on the signal that's being processed. So that's why we include it, because it's much more realistic than leaving it out. The practical resistances either create a voltage drop in a practical voltage source or a current drain if you've got a practical current source. So let's look at an example. In order to determine what the output voltage is, the output voltage is just going to be the voltage division between the load resistance and the source resistance. So V out is going to be RL over RL plus RS times Vs. So in order for V out to be approximately equal to Vs, which is what we would like, the source resistance needs to be much, much lower than the load resistance. In the case of a practical current source, we have a source resistor in parallel with a load resistor. And in order to figure out what the output current is, we just use current division, meaning that we take the parallel equivalent of RL and RS, and divide that by RL, and multiply that by the source value. So in this case, the source resistance needs to be a lot higher than the load resistance in order not to drain a significant amount of current. So that's why we represent the sources in this way. Amplifiers we talk about a lot in this class. Amplifiers are basically used to make small signals larger. And there are many, many, many reasons why we might want to do that. But in general, we want to amplify voltage, current, and power. They're all amplified. It just depends on what we're actually looking for. And the gain, or the amount of amplification for voltage, current, and power, can be different for the same amount for the same amplifier. So you could have an amplifier that gives you twice the voltage out, but then it gives you a quarter of the current. So it just sort of depends on how the circuit is designed in order to determine how the relationship of the gain is going to be. So a linear amplifier is basically characterized by the fact that V out is equal to some type of multiplier gain, A, times V in. So the value of A is just going to be a number. It could be a positive number, it could be a fraction, it could be a negative number, it just depends on the situation. But that gain is going to always be just a linear relationship. A nonlinear amplifier would have higher powers of Vn at the output. So you might have Vn squared or Vn cubed. We generally are not going to deal with amplifiers that are non-linear in this class. Generally, all the amplifiers will be linear. Different symbols are used to represent amplifiers depending on how we want to look at it. The symbol used to represent it might be how it's connected or whether we've simplified it, Both of these symbols are the same. They're basically telling you that there's going to be an input and the output is going to be magnified by a certain amount. And basically the one on the left is more general than the one on the right. The one on the right actually has a common ground reference and is going to be used a little bit differently. But either one is basically representing that there's some kind of input voltage and it's giving you some kind of output. The gain of the amplifier, if we look at the symbol here, there are input and output values as shown. We have Vn and some kind of input current going into this amplifier, and we have a current coming out and a voltage out. So the voltage gain is just going to be the output voltage divided by the input voltage. This is a value that, since it's volts divided by volts, you can have units of volts per volt or you can have no units. It doesn't matter to me. Either one of them is going to be fine. Oftentimes people use something like volts per volt in order to tell that it is a voltage gain, but usually we'll know that. So I'm not super picky about whether you put volts per volt or no units at all for voltage gain. Current gain is just the output current over the input current. Again, this is going to be just a number or amps per amp. Either one is fine. And then power gain is going to be power out over power in. And that can be reduced to V out times I out over Vn times In, which basically just gives you AV times AI, and that will give you the value of power gain. Transfer characteristics are something we use frequently in this class to show the relationship between the input and the output of an amplifier. So in this case, the slope of this particular line is V out over Vn, and that gives us the gain of the amplifier. And that can be useful later on when we look at different types of amplifiers and how they work. Oftentimes, it's useful to represent gain in decibels. We do that for a large number of reasons, but decibels is a logarithmic measure, and it initially was applied to power, and related kind of how power works. So if you double power, you're basically increasing the power by 3 decibels. If you take half the power, you're decreasing the power by 3 decibels. So oftentimes in amplifiers, we want to look at where half power points are, and that's when the power is 3 decibels less than the maximum value. And it's a little easier to find that graphically and represent that if we're using decibels versus trying to find halves and such and so forth. So in order to find the gain in decibels, for voltage gain, we take 20 log times the magnitude of the voltage gain. And for current gain, it's the same way. We take 20 log times the magnitude of the current gain. Power gain is just slightly different. We actually have 10 times log of the power gain. And the reason that we have 10 and not 20 is because power is related to voltage or current by a square. So if either is doubled, it quadruples the power. So we only multiply by 10 instead of 20 for that reason. Most of the gain in this class is voltage gain. Why? Basically because it's really easy to measure voltage in and voltage out of something and compare the two values. It's a little harder to measure the current. It is even harder to measure the power. So oftentimes we will measure the voltage into a system and the voltage out of a system and characterize it by its voltage gain. Oftentimes in finding dB values, we get negative gain values. And what this means is that the circuit is actually producing a signal loss rather than a signal increase. So if the gain is a negative dB value, it just means that it is reducing the value out rather than increasing it. So let's look at an example. And we have an amplifier at 1 kilohertz that has a 1 volt peak input signal, and it drives a 0.1 milliamp into the amplifier. Then we get 8 volts out across a 1 kilo ohm load, and we want to find the voltage, current, and power gains, and then to find those values in dB. So we have Vn equals 1 volt peak. And we do like to pay attention to whether it's peak or peak to peak. That's going to make a difference. We know that In is equal to 0.1 milliamps, and we're also going to assume that's a peak value because the value given in voltage was peak, so we're going to assume that that's also a peak value. The out is going to equal 8 volts, and again, that's a peak value. And we don't know I out, but we do know RL, so we can figure out I out in a minute. So the voltage gain is going to be V out over Vn, which is going to be 8 over 1, which equals 8. And if we want to change that to decibels, we take 20 times the log of 8, and that gives us 18.06 dB. So that is the gain for the voltage gain. The current gain, first we need to find the output current. The output current is going to be V out over RL. So that's going to be 8 volts divided by 1K, and that gives us 8 milliamps. So AI is going to be I out over I in, which is going to be 8 milliamps over 0.1 milliamps, and that's going to give us 80. And if we want to find the log value of that, or the dB value, we take 20 log of 80, and we get 38.06 dB. So you notice that the voltage and current gain are very different. Even though it's one circuit and one amplifier, it has a very different way of processing the voltage and current. The power in, to find the power gain, is going to be 1 volt times 0.1 milliamps. So that's going to give us 0.1 milliwatts. And the power out is going to be 8 volts times 8 milliamps, which is going to be, or 64, sorry, milliwatts. So that means the power gain is going to be P out over P in, which is going to be 64 milliwatts divided by 0.1 milliwatts, which equals 640. So the value of the gain in dB is going to be 10 log of 640, and that gives us 28.06 dB. If we change the frequency, we don't look at this much in this class, but if we change the frequency, it's going to change how the amplifier works. And a lot of times amplifiers will work one way at one frequency, and they may work differently at another frequency. So in this case, the same amplifier is now getting 0.1 volts peak output voltage. And if we want to find the voltage gain there, we take V out, which is 0.1 volts. We divide by V in, which is 1 volt, and that gives us 0.1. And if we want to find the dB value, we take 20 log of 0.1, and we get negative 20 dB. So that's basically how it looks when you have a circuit attenuation going on. Other things that happens in amplifiers. Amplifiers actually have a maximum output signal value that they can have. They will amplify linearly until they reach something called saturation. And at saturation, you can increase the input voltage, but the output voltage doesn't change. The reason for this is the range of the power supply that's running the system. All amplifiers have certain power characteristics. They need an external power supply to operate, and that actually produces a limitation in how the circuit will process the signal. So if we look at the transfer characteristics for a typical amplifier, this is a linear amplifier. So for values of Vn that are intermediate, V out will be undistorted. So V in comes in, and it is relatively, it's within the limitations of the circuit, it seems. And so what you get out is bigger, but reasonable. It's not distorted or anything like that. If we send in a signal that's too large, so you notice that the input signal actually goes outside the boundaries of where the amplification can occur. What happens is the output gets clipped. So the positive and negative value of the output actually gets flattened because it can't go above the power supply. So that's one of the limitations that amplifiers will have. You will see many, many more ways that amplifiers work. These are sort of the very, very basics that hold for all amplifiers. Then when we look at different types of amplifiers, you'll see that they have different characteristics as far as what amplifier you're using. But in general, this is how they work.